Welcome to AI Paper Podcasts. Today we are tackling AgentEvolver, towards efficient self-evolving agent system from Tanguy Lab at Alibaba Group.
And this paper is really a direct answer to the three huge bottlenecks we see with LLM-based agents right now.
Right. First, the insane cost of creating data. Second, the total inefficiency of exploration.
And third, how poorly training samples are used because the rewards are so sparse.
So what AgentEvolver does, and this is the core idea, is it shifts the entire learning process onto the LLM itself. It's like a fully autonomous loop.
Exactly. They get away from those rigid manual pipelines and build this system around three really synergistic ideas. The first is self-questioning.
So the agent generates its own tasks.
Then you have self-navigating for much smarter exploration. And finally, self-attributing, which is all about assigning credit and rewards in a much more fine-grained way.
And the headline result here really proves that agent intelligence isn't just about throwing more parameters at the problem.
Not at all.
AgentEvolver gets better task completion on really tough benchmarks like AppWorld, but, and this is the kicker, it does it with way smaller models.
Yeah, we're talking about their Qwen 2.514b model, with AgentEvolver outperforming the baseline Qwen 3.235b model.
That is a massive win for efficiency. It's proof that a smarter learning process can be worth more than just raw model size.
It really is. So let's start with that first bottleneck, data scarcity. How do you get training data for a brand new environment?
This is what their self-questioning module, or for task, as they call it, is designed to solve.
Right. The challenge is, you can't just manually create thousands of complex, diverse tasks. It's just prohibitively expensive and time-consuming.
So what AgentEvolver does is it uses this idea of curiosity-guided exploration. The agent gets what they call an environment profile.
Which is basically just a summary, right? Like a little map of what's in the environment.
Exactly. It lists things like hospitals or traffic lights and the actions you can take, like move or wait and cross.
And with that map, the agent, using a high-temperature LLM, you can think of it as being in like a creative or stochastic explorer mode, starts poking around the environment.
And they have this two-phase strategy. It starts broad, just to get a lay of the land, before it switches to a more depth-first search.
Yeah, and it uses this myopic rule, considering only the most recent observations. This is clever because it stops the agent from getting lost down some long, pointless rabbit hole too early on.
Okay, so it explores, it finds something interesting. The next step, adaptive task synthesis, is where the magic really happens.
It is. That exploration path, the successful one, is immediately turned into a structured task query.
And here's the key technical detail. That original exploration trajectory is automatically set as the proxy ground truth solution.
Yes, this is so important. The system invents a new problem, and in the same breath, it creates the answer key for it.
This gives it a reference point, something to judge against later.
But I have to ask, doesn't this just shift the problem? You have one LLM inventing tasks and another, bigger LLM, the judge grading them. What about hallucinations? How do you know the task it invented is even possible?
That's a great question, and they have a really solid answer for it. They use multi-layer filtering. So beyond the basic stuff like deduplication, they have this really strict feasibility assessment.
Okay, what does that involve?
Before any training starts, they actually try to run that proxy ground truth solution. If the reference solution itself fails, they just toss the whole task out.
So they're weeding out the hallucinations right from the start. That's smart. It ensures the quality of the synthetic data.
Exactly. So assuming the task is feasible, they now need a reward signal. This is where that LLM judge comes in to generate a synthetic task reward.
Right, because in these new environments, the true reward is probably sparse, or you just don't know what it is.
And they don't just ask the judge for a simple thumbs up or thumbs down. It's way more sophisticated. It does continuous scoring. It checks for how efficient the steps were.
And it gives an immediate 0 score for any redundant or totally irrelevant actions.
And most importantly, it uses that proxy ground truth solution we were just talking about for a reference-based correctness check. It makes sure all the essential steps from the original successful run were actually included.
The practical result of all this is huge.
Totally. Their experiments show that when they trained their 14B model on a hybrid data set, so a mix of the original human data and this new synthetic data performance just jumped.
So it's not just about more data, it's about better, more diverse data. It's expanding what the agent knows is possible.
Precisely. So task scarcity is, more or less solved. That brings us to the next big challenge, rollout inefficiency.
Yeah, traditional RL is just so expensive. You're doing these repetitive, random trial and error runs.
And if each of those rollouts costs you real money in compute, you can't just let it run forever. This is what their self-navigating component is all about.
So self-navigating is all about learning from experience, but they have a very specific definition of experience.
It's not just the raw data from a successful run. It's structured natural language knowledge that's been distilled from past attempts.
It has two parts, a when-to-use trigger, and then the content, which is the actual instruction, like a reusable piece of wisdom.
Right, like always verify an API exists before you try to call it. A simple rule, but incredibly useful.
So during the experience acquisition phase, these little nuggets of wisdom from both successes and failures get validated and then stored in a vector database.
And when the agent starts a new task, it retrieves the most relevant experience, refines it a bit, and then injects it right into the prompt. It's like giving it a hint.
It acts as an in-context learning, or ICL, signal to guide that specific rollout.
This leads to their experience mixed rollout, where they balance pure exploration, the vanilla attempts, with this guided exploitation, usually about a 50-50 split.
But here comes, I think, the most brilliant technical trick in the whole paper.
Experience stripping.
Yes. So wait, they guide the agent to a successful outcome using this piece of curated wisdom.
And then right before they start training the policy, they delete the wisdom. They literally strip those tokens out of the training data.
That sounds so counterintuitive. Why would you remove the very thing that led to success?
Because if they left it in, the model would just learn to cheat. It would overfit to copying the external text.
So by stripping it, you force the agent to actually internalize the logic, to make that external hint part of its own internal reasoning.
It's transforming explicit guidance into implicit knowledge, but as you can imagine, this creates a problem.
Yeah, an off-policy mismatch. The rollout was done with a hint, but the training update is calculated without it. Normally, your algorithm would just clip away that successful learning signal.
To fix that, they use something called selective boosting. Only for the successful experience-guided samples, the ones with a positive advantage, they temporarily boost the upper clipping threshold of their policy algorithm.
So they're basically widening the goalposts just for those specific samples to make sure that valuable signal is preserved.
Exactly, and their validation shows this is what makes it all work. This implicit RL training with selective boosting blows away just using the hints explicitly with ICL.
It's actually learning to generalize, not just follow a prompt. And that means fewer wasted rollouts, which means massive compute savings.
Okay, so we've got data generation and efficient exploration covered. That leaves the final piece of the puzzle. Self-attributing or fair reward.
Right, and this tackles the problem of low sample efficiency. If you have a 50-step task and only get a single reward at the very end.
Every single action gets credited equally. The brilliant step and the disastrous one both get the same tiny fraction of the final reward.
It's just wildly inefficient. Self-attributing is designed to shift from that slow, delayed credit assignment to an immediate contribution-based system.
So how does it work?
They use the LLM judge again, but this time it looks back over the entire completed trajectory, the task, the actions, the final outcome, all in one go.
And it gives every single step a label. Good, which is a +1, or BAD, which is a -1.
It's based on whether the action actually helped, was irrelevant, or, made things worse.
This creates a really dense step-by-step signal about the quality of the process itself.
But the key detail is how they normalize this signal. Instead of normalizing across every single step in the training batch, they standardize at the trajectory level.
Why is that important?
It stops longer trajectories or a few outlier steps from completely skewing the statistics for the whole batch. It's a much more stable signal.
So they have this process quality reward, and then they create a composite reward by fusing it with the final outcome reward.
And they normalize these two signals separately to make sure their individual contributions are preserved.
Which gives you their final reward equation. A weighted blend of the attribution reward at every step and the outcome reward at the very last step.
And that weight is controlled by a hyperparameter, alpha. This brings up a really fascinating trade-off.
Yeah, if you set alpha too high, the agent stops trying to solve the task and starts trying to please the judge.
Exactly. It overfits to the judge's specific heuristics about what a good process looks like, and its final performance on the actual task can get worse.
So they found a sweet spot for alpha, between 0.10 and 0.20, that balances learning a good process with actually achieving the final goal.
And the efficiency gains from this are just staggering.
They're huge. Using self-attributing, cut the number of training steps needed by 55 to 67%.
So you need less than half the training steps to get to 90% of the baseline's best performance. If you're a team paying for that compute, that's game-changing.
Absolutely. Now, before we wrap up, we have to touch on the infrastructure that actually makes all this possible, especially for these long horizon tasks.
In the context manager, or CM?
Right. Managing memory is critical. The CM has two main parts: a live context timeline, which is the agent's working memory.
And the timeline snapshot recorder, which is like an immutable permanent record of everything that happened.
And on top of that, they define different context managing templates, or CMTs. They tested a few, but the one that really stood out was the self-context managing template, the SCMT.
What's special about that one?
It's the most autonomous. When the agent's context window gets full, the policy LLM itself gets to decide what to do.
So it can choose to keep a message, remove it, or compress it.
Exactly.
Yeah.
This is so powerful in environments that can spit out hundreds of lines of useless debug text. The agent learns to actively manage its own memory and stay focused on what's important.
And the SCMT got the best performance, which confirms that for really complex tasks, you need the agent to have control over its own attention and memory.
So to bring it all together, AgentEvolver is this beautiful closed loop. The agent makes its own homework with self-questioning.
It learns faster by using cheat sheets from past successes with self-navigating.
And it grades itself with near-perfect accuracy using self-attributing. It tackles the three big bottlenecks: cost, scarcity, and efficiency.
Looking forward, the really exciting next step is what they call LLM-level self-evolving.
What does that mean exactly?
It means unifying all these different parts: the exploration, the attribution, the policy updates, inside a single model, or at least a very tightly coupled family of models.
So you'd have these knowledge maintenance loops that are almost instantaneous. The model is constantly generating tasks, grading its own performance, and updating its own internal reasoning, all within itself.
It's the path towards an agent that can truly perpetually refine its own skills and knowledge.
And for you, the listener, if you're building things like enterprise automation agents, think about this. That self-questioning mechanism could completely revolutionize how you generate test data.
Absolutely. You could have the agent itself manufacture thousands of robust, complex test cases for your multi-API workflows. You wouldn't need an army of human testers to write them. The agent literally writes its own textbook.